Welcome to the third lecture on diffraction of light. In this video, I am going to discuss about Fraunhofer diffraction due to a double slit. Before proceeding to this video, I would request you please watch the previous video on Fraunhofer diffraction due to a single slit. Till now, we know what the Fraunhofer diffraction is. Let's consider that we have a plane wavefront AB which is of a monochromatic light of wavelength lambda and frequency omega, and this plane wavefront incidenting on a slit. Basically it's a double slit, that means two openings. Okay, so this is called a double slit. Once this plane wavefront incident on this slit, then we can consider this part of that wavefront as a primary wavefront. Okay, secondary wavelet start from this primary wavefront and they will interfere to produce a diffraction pattern. To observe that diffraction pattern, we can place a screen. Now we all know for the Fraunhofer diffraction pattern, it is necessary that the object and screen must be at the infinite distance from the diffracting object. That means from the slit. The object is at infinity, that's why we are getting a plane wavefront. And to place the screen at infinity, we can place a convex lens in between the slit and screen such that the screen will be at the focal plane of this convex lens. In that way, we can ensure that incidenting light coming from left to right will see this screen at the infinite distance. Okay? Now, let's assume all the secondary wavelet traveling normal to the slit, that is parallel to this red dashed line, are brought focus at point C. Okay, and any other secondary wavelet traveling at angle theta with this red dash line are brought focus at point Q. Okay, just consider a center point of this lower slit O. Now we need to calculate the intensity of light on this screen so that we can understand the diffraction pattern. Okay, to do that, we first need to calculate the intensity at point Q, which is a function of theta. Then just by varying the whole theta, we can calculate intensity of light at any point on this screen, right? To do that, we need to do some mathematics. Okay, we just consider a diffracting element dx, which is in between this slit somewhere, and let's suppose this light is coming from O and another light which is coming from this diffracting object dx from a point P, and then we just draw a perpendicular on this line from the point O so that we can calculate the path difference between the light coming from point O and light coming from point P. Why I am doing that, it will be clear in a minute. Just ask a question to yourself. What is the disturbance of light at point Q due to light coming from point O? And the answer will be A e to the power I omega t. Why? Because we know any wave can be represented as A e to the power I omega t minus kx, where k is the wave number, x is any position in space. As we are observing at a particular point Q, that space part will become constant and we can absorb that space part in the constant A. Therefore, the complex light disturbance at point Q at any instant due to light coming from point O will be A e to the power I omega t. Now the next question is, what is complex light disturbance at point Q due to light coming from a point P? To do that, we just need to calculate the phase difference between the light coming from point O and light coming from point P. The phase difference is nothing but 2 pi by lambda into path difference. Path difference between the light coming from point O and point P is Pn. Just look at this smaller triangle and we know the angle between PON is theta, and if the distance of O from the point P is x, then Pn will be x sine theta. Now just assume that 2 pi by lambda sine theta is equals to L. Therefore the phase difference will be L into x. Now it's very easy to write down the complex light disturbance at point Q due to light coming from point P. We just need to include this extra phase. Therefore the complex disturbance at Q due to light coming from point P will be proportional to e to the power I omega t minus Lx. This extra phase which I have included here. Now the next question is, what is complex light disturbance at point Q due to light coming from the diffracting element dx? And it is very easy for us. we can easily guess larger the width will be, more will be the disturbance. Therefore, disturbance will be proportional to dx. So we can simply write the resultant disturbance at q at any instant due to light coming from element dx will be dy. Let's represent that as dy. Therefore, dy is equals to k a e to the power I omega t minus lx into dx. Here k is proportionality constant. Okay. Now the final question. What is the complex light disturbance at point Q due to hole slit? That is from these two slits, okay? The lower one and the upper one. Because it's a double slit, so we can write that as y. And now we have to integrate it over whole x. Therefore, just integrate it as O is the center of this lower slit and A is the slit width. Then we can integrate for the lower slit between minus a by 2 to plus a by 2. Okay, so this is the contribution coming from the lower slit minus a by 2 to plus a by 2 ka e to the power I omega t minus lx into dx. Plus, now take the contribution from the upper slit. As any two points corresponding points in the two slits are separated by a distance of d, right? So just check the lower point of the lower slit and the lower point of the upper slit are separated by a distance of d. D is a plus b. A is the width of the slit, b is the width of opaque space. Therefore, any corresponding points are separated by a distance of d. Therefore, just introduce this d in the limit d minus a by 2 to d plus a by 2. So this is the complex light disturbance at Q. Now we can calculate the intensity by solving this, and then just by varying theta we can calculate the intensity at any point on this screen. So let's solve it. It's a very easy integration. Look at here carefully, as this integration is over dx, so we can take out k capital A e to the power I omega t outside of this integration and then just perform it and substitute the limit. You will get this y is equals to ka e to the power I omega t, this factor for the first integration, plus ka e to the power I omega t, this factor for the second integration. Now look at carefully, there is a common between these two terms. Just take that outside, ka e to the power I omega t e to the power minus I la by 2 minus e to the power I la by 2 divided by minus IL. So here we will have 1 is here, and from here we can get e to the power ILD. Okay, look at this term carefully. We can represent this term in the sine function, right? E to the power I theta minus e to the power minus I theta is equals to 2I sine theta. We will use that relation and we can simply write this factor as Ka sine La by 2 upon La by 2. Here we have introduced small a. To do that, we have multiplied small a here because we want to see this kind of relation, okay? And this extra 2 came because if you represent this numerator in the sine function, you will get 2 sine. So that 2 is here. And now this term is as it is. This is the disturbance. So to calculate the intensity, we need to multiply the disturbance by its complex conjugate because this is a complex number. Just multiply y with y star. This will give you the intensity. You will get this expression where alpha is equals to La upon 2. Okay, and I naught is Ka small a whole square. Now look, this expression getting nicer and nicer. Now again in next step we need to replace this exponential term in the cosine function because e to the power I theta plus e to the power minus I theta is 2 cos theta. We will use that relation and the expression will look like I equals to I naught sine square alpha by alpha square times 2 plus 2 cos LD. We can take this 2 outside, so we will have 1 plus cos LD. Then we can again use the formula of cos 2 theta and we can get 1 plus cos LD is equals to 2 cos square LD by 2. Okay, and then we use LD by 2 as a beta. Therefore, this expression will reduce like I is equals to 4I naught sine square alpha upon alpha square cos square beta. So this is very important relation. This is intensity due to double slit diffraction at any point. Okay. So just by varying theta, as alpha and beta depend on L and L depend upon theta. So if you change the theta, this alpha beta value will change and accordingly the intensity at that point will change. So by using this relation, we can calculate the intensity on the screen at any point. Okay. Now let's try to understand this intensity expression. Look at this expression, sine square alpha by alpha square. What is this? If you have watched my previous video on Fraunhofer diffraction due to a single slit, then you can easily guess this is nothing but intensity expression of a single slit. So this term sine square alpha by alpha square gives you the diffraction pattern of a single slit. Along with it, we have another term cos square beta. What is this? This gives you interference pattern of diffracted light from two slits. Here we have two slits, right? One slit is diffracting the light in its own way. Another slit is also diffracting the light in its own way. And then those diffracted light from two slits can interfere, right? And they are producing the interference pattern. So we are having here the diffraction pattern, at the same time they are producing interference pattern too. So both are overlapping, and then finally we are getting pattern which we are calling diffraction due to a double slit. Okay. In the later part of this video, we will see how this intensity pattern will look like. Okay. Before trying to figure out how the intensity pattern will look like, we need to calculate few fundamental things, that is condition of diffraction maxima and minima. Why I am calling it diffraction maxima and minima? Because here we have two different kinds of light. One is diffraction, another is interference. So we need to calculate the condition for maxima and minima of the diffraction as well as from the interference pattern. Okay. For the diffraction, we need to just take a derivative of diffracting intensity with respect to alpha to 0, because the diffracting intensity depend upon alpha, sine square alpha by alpha square. So just take a first derivative to 0 and you will get sine alpha equals to 0 and tan alpha equals to alpha. Till now we know that sine alpha equals to 0 and tan alpha equals to alpha can be a condition of maxima or minima. To verify whether it belongs to maxima or minima, we just need to calculate the second derivative, and if the second derivative is less than 0, then that condition will be for the maxima, and if it is greater than 0, then condition will be for the minima. And if you do that, then you will find out that sine alpha equals to 0 will be the condition for minima, and tan alpha equals to alpha will be the condition for maxima. We know now what is the condition for minima and what is condition for maxima. But be careful, this is the condition for minima and maxima for the diffraction pattern. Okay. Now come to the interference maxima and minima, because we have interference term too, that is cos square beta. So to find out minima, we just need to check the minima of cos square beta. And when cos square beta will be 0, what will be the minimum value? Minimum value will be 0, because this is a square term, and it will be 0 when cos beta equals to 0. And cos beta equals to 0 means beta has to be odd multiple of pi by 2. Therefore, we can take beta is equals to plus minus 2s plus 1 pi by 2. Here s will be from 0, 1, 2, 3, 4, a positive integer. Okay. And now just try to write it down in the terms of theta, because theta is actual our parameter. We know beta is equals to LD by 2. L is equals to 2 pi by lambda sine theta. Just substitute it here and you will get a plus b sine theta is equals to plus minus 2s plus 1 lambda by 2. So this is the condition of interference minima. Now the condition for maxima. And cos square beta can have a maximum value of 1. Therefore cos beta can be plus 1 or minus 1. Therefore beta can be p pi, that is the integer multiple of pi, and p can be 0, plus minus 1, plus minus 2, and so on. Just figure out this formula, just substitute the value of beta in terms of L and then substitute L in terms of theta, and you will get a plus b sine theta is equals to p lambda. These two are the condition for minima and maxima of the interference pattern. Okay, remember it is for the interference pattern. Now look into the detail of minima condition of diffraction pattern. We just got sine alpha equals to 0 is the condition for minima. Therefore alpha has to be integer multiple of m, and m can be plus minus 1, plus minus 2, plus minus 3. Why not 0, right? That's a question. Because when alpha tends to 0, sine square alpha by alpha square will tends to 1. Okay. So in the limit alpha tends to 0, Sine square alpha by alpha square tends to 1, that is maxima, not the minima. And we will see that for m equals to 0, that will be the condition of principal maxima. Just substitute the value of alpha in terms of L and then substitute the L in terms of theta. We will get A sine theta equals to m lambda. This is condition of diffraction minima. Just try to memorize all these relations. Now look into detail of maxima condition. We know tan alpha equals to alpha is the condition for maxima. And as this is a transcendental equation, it will be very difficult to solve this analytically. Here we will take the help of graphical method so that we can find out the value of alpha which satisfies this relation. And to do that, we just need to plot two curves, one for tan alpha, another for alpha. So here these curvy lines are for the tan alpha and this straight line passing through 0 is for the alpha. And all the intersection point of tan alpha with the alpha will be the solution, will be the alpha. Okay. So just plot these two curves with alpha as a independent parameter and y as a dependent parameter, and just plot that. And here you can see the very first cut point is at alpha equals to 0. Therefore alpha equals to 0 is condition for maxima. Okay. And that we call principal maxima. Let's try to find out another cut point, that is somewhere here, which is approximately equals to 3 pi by 2. Not exactly. Then another one approximately equals to 5 pi by 2. So the other values of alpha for which this equation is satisfied, that is approaching to plus minus 3 pi by 2, plus minus 5 pi by 2. So these are the values of alpha for which we can get the condition of maxima. Now we are very close to find out how the intensity pattern will look like, because now we have a clear idea about the position of maxima, position of minima, and so on. So before proceeding to that, before plotting that intensity pattern, let's see another important concept which we will use while plotting, and we will verify this also. This is very important concept, missing order. What is that? Here we know the first part is for the diffraction and second part is of the interference. Okay, and this is the condition for diffraction minima and this is the condition for interference maxima. So if you look that equation carefully, the both equation, for a particular value of theta, depending upon the value of m and p, that both condition can satisfy simultaneously. So from here we can say, if two conditions are simultaneously satisfied for a given value of theta, then the corresponding interference maxima will be missing. Why? Because the diffraction intensity is multiplied with the interference intensity. So if diffraction intensity will be 0, then you can multiply any quantity with the 0, it will be the 0. Okay. Therefore, we will have a minima instead of maxima. Now note it carefully, we are talking about the interference maxima. So if these two conditions are satisfied simultaneously for a given value of theta, then corresponding interference maxima will be missing, and that we call missing order. How we can find out the missing order? For a given value of theta, just divide the equation 2 by equation 1, then we can get a plus b by a is equals to p by m. Now suppose the structure of your double slit is such that the opaque space is twice of the slit width, that is b is equals to 2 times of a. Then if you substitute here, a plus b by a will be 3. That means p is equals to 3 times of m. So what it means? It means third, 6, 9, etc. order of interference maxima are absent, which corresponds to first, second, third order of diffraction dark band, that is diffraction minima. So when the first order diffraction minima will come, corresponding third order of interference maxima will be missing. We can verify it. Now let's just plot this intensity pattern. So this is our final intensity relation. Just substitute the first part, that is the intensity due to the diffraction, and we can have this kind of intensity pattern. And this we know, we have already seen this in the Fraunhofer diffraction due to a single slit. Now just plot separately the intensity due to the interference pattern, and it will look like this. Now just multiply these two, and here I have assumed same thing, that is b is equals to 2 times of a. So now my actual intensity will look like this, the red line. Okay, This is my actual intensity which I will observe on that screen, and it will have an envelope. So envelope is due to the diffraction, and the actual pattern you can see like this. Now look at here carefully. This is the central maxima, that is the principal maxima of the diffraction. This is the first diffraction minima. This is the second diffraction minima around 2 pi. Now look at the interference maxima. This is your first order interference maxima. This is second order interference maxima, and third order is missing from here. This is the fourth order, this is the fifth order, and sixth order is missing. Right? So here you can easily check that for the first order of diffraction minima, third order of interference maxima is missing. And that's what we are talking about, the missing order. So hope all this concept related with the intensity pattern, the calculation of intensity and missing order, everything is clear to you. In the next lecture, we will discuss about the intensity pattern due to a diffraction grating, and then finally we will see some of the numerical problem related to this topic. Okay. Thank you. See you again.